Alright, hey guys, what's going on today? We're going to be talking about complex manifolds a little bit more, and this time we're going to wrap up our discussion on holonomy, and then we're going to move into some more meaty mathematics on quantum gravity. So with that being said, let's get straight into the topic, and make sure to hit that like and subscribe button. Make sure to go into my Patreon page if you want to support the channel and get these notes, and if you want to see member-only content and early content, you can become a member on this YouTube channel as well. So without further ado, now let's get into the topic. So today we're going to be talking about complex manifolds and holonomy. We want to first talk about fiber bundles. So fiber bundles are a very, very important type of mathematical structure in physics, and we're just going to briefly touch upon them in this video, and then maybe in later videos we'll go deeper into them. I'm just going to provide a couple of examples because understanding fiber bundles is key to understanding quantum gravity, at least to some level. Okay, so we're going to start off by considering these three different types of manifolds: the E manifold, an M manifold, and an F manifold, and all of these are linked together in some way. Okay, the E manifold is called the bundle, the M manifold is called the base, and the F manifold is called the fiber. Okay. Now let's take some examples of this. And this will really help us solidify our understanding of what a bundle is. Really what a fiber bundle is a manifold embedded inside of another manifold. Okay? So we're going to take our base as being just the circle, S1 circle, and we're going to take our F manifold as just being the line, or the one-dimensional line of values going from -1 to 1. Okay, so our base manifold is the circle, and then we have our one-dimensional manifold radiating from the circle. This is why we call it sort of a fiber bundle. It looks like a fiber. You have these things attached to a base manifold. So the base manifold again is S1, and these lines are lines going from -1 to 1 and 0. So all the integers are going from -1 to 1. Okay, it doesn't necessarily have to be -1 to 1. It can be 2 to 1. It can be, or not 2 to 1. It can be 1 to 2. It can be 2 to 10. Whatever. The point is that we've defined a manifold F inside of another manifold M. Okay. The transition functions between the atlases on the base manifold M are just the identity, meaning that there's no twists or turns anywhere along the base. However, we can consider a Mobius strip. A Mobius strip is another example here. It's a similar structure, right? The base manifold is S1, and F is the fiber bundle, or the fiber, and but however, there's a difference. The difference here is that at one of the transition points, the transition function is z to -z. So there's a flip in the bundle. Okay. So, and that's what a Mobius strip is. Okay. If you're not aware of what a Mobius strip is really just it's a one-sided surface. It's a topologically interesting surface. Okay. It's a one-sided topologically interesting geometric object. Okay. And we're not going to go into Mobius strips here, just to say that this transition function is really what makes it unique. Okay. So there's some different categories of bundles. We're going to classify these bundles very briefly, just to really solidify our understanding of these. If F is a vector space, then we have a vector bundle. Okay. And an example of this is a tangent bundle. So in GR, in general relativity, we're talking about the entire collection of tangent spaces, all at the points along the manifold, right? So you have this base manifold that we've talked about, which is the four-dimensional manifold, and at every point you have a tangent space, and that tangent space is a vector space, and so we call this a vector bundle, specifically a tangent bundle. Okay. We can also consider Lie groups, right? So Lie groups can be orthogonal to each other, therefore creating something of a vector space, but they're groups. They act on things. And so when they act on things, we have these matrices, right? So these U1, SU2, or SU3 gauge groups that can form their own sort of internal spaces on F or on the manifold. Internal spaces, I like to think of F as internal spaces, right? Because you have the base manifold, and then you have internal spaces at each point on the manifold. Okay? And we're going to really talk about this in quite depth when we start talking about triads, tetrads, and so forth, okay? But the point here, again, is just that if it's a Lie group, in other words, a set of operators that obeys the Lie group, then we have a principal bundle, okay? And so here's our base manifold M, and we can have vector spaces, or we can have a Lie group at each space. Hey guys, what's going on? If you're interested in this video and want to learn more about loop quantum gravity, string theory, and so forth, what you can do is you can become a member of this channel, and you can gain access to all the videos that become uploaded on this topic and future topics as well. Again, thank you so much for your support, and thank you so much for watching. This channel keeps on growing and growing, and I'm very excited to see where this is going to go in the future. So with that being said, make sure to hit that like and subscribe button if you like this kind of content. Make sure to become a member as well. Thank you, and bye.